a polyhedron. Remember, when I say the word quadrilateral, what figures could fall underneath that? Square, rectangle, rhombus, trapezoid, right? There's a whole bunch that could fall under there. Well, when I say polyhedron, these all here are all types of polyhedrons. Okay, these are all types of polyhedrons right here. Three-dimensional figures. And every polyhedron comes with a face, faces, edges, and vertices. They always come with those three. A face, they're not sides, but you can think of it that way. This right here is a face, all right, of my polyhedron. Every face is connected with edges. So in this case, BF would be an edge. Every edge has two vertices. H, E, G, those are all vertices. All right, so what I want to do with you first, I got three polyhedrons up there. I want to see if we know what they are, and then find the number of faces, edges, and vertices each one has. Anybody know what you call number one? Cube, yep. All fancy square prism, aka a cube. So first thing I'm going to ask somebody today, first question, first number of the day. How many faces does this bad boy have? All right, how many faces does this have? Remember what a face looked like up here on my polyhedron? How many faces on this cube? Let's start us off right. 3? 6. There we go. All right, how many edges? And I'll let you know a common mistake with edges, people count the same edge twice, so be careful. Oh, 1, 2, 3, and they keep counting the same ones again. All right, count them once, count them once. All right, how many edges up here in my cube? Woo, 14? 12, thank you. 12 edges. And how many vertices? Again, be careful. Very common mistake is to count the same vertice twice. We don't want that. How many vertices does this cube have? Oh, 10? 8. Good work, everyone. All right. Next figure. What do I call that bad boy? That's pyramid. Yep, we'll talk more about those tomorrow. But for now, how many faces does this pyramid have? How many faces? Faces. 7. Not here, thank you. I will remember that now. 24. 5 faces, good. How many edges? Be careful, take your time. 12, how many edges? 8. And then count the vertices, more than just that top point. 13. Thank you. 3. 5 vertices. Good. All right. Anybody know what I call number 3 up there? Prism. Prism. That is called a prism. Anybody know what type of prism it is? We're going to talk about this today. Ooh, triangular. Why do I call it triangular and not any other shape? We'll talk about that in about 5 minutes. But for now, go ahead and find the faces, edges, and vertices for me if you haven't already. And then we'll talk about a little check. How do I know I have the right amount and I didn't double count an edge or a vertex? Oh. How many faces on my triangular prism? 4? 5? How many edges would I have on my triangular prism? 8? Not. Oops, sorry. Go ahead. 9. Thank you. Oh, now I'm rattled. Got it. 9. And how many vertices? 14? 6 vertices. Now, I mentioned it's easy to double count an edge or a vertex. Somebody may have did it during one of these 3 examples. So how about a little check just to make sure, if you want to see that you counted the correct amount. And I'm not going to take credit for this check. I want to introduce you to my boy here, one Mr. Leonard Euler, famous mathematician in the 1700s. He did all these polyhedrons and he looked at the faces, edges, and vertices, and there was a pattern that he noticed. All right. How about that Leonard spelling? And then it's not Euler, it's Euler. That's legit. Okay. Leonard Euler. He found a little pattern. All right, he found a pattern. Here was the pattern, and this is how you can check to make sure you didn't double count. You could take the number of faces and add that to the number of vertices, and then subtract out the number of edges. So add your faces and vertices, subtract the edges, and I don't care what polyhedron it is, every single time your answer is 2. Every time. You could try it on one of the 3 we just did. Every time it's 2. All right, so that's how you can check. All right. Now, just a warning, I would not use this check. Let's say you found the number of faces and edges and you're using this to find the number of vertices. I wouldn't do it that way because what happens if one of these are wrong? Okay, I would do it, find all 3 and then use your check. All right, so Leonard Euler, props to you. Questions on faces, edges, and vertices, because I have a new concept now. Cross section. Cross section. All right, everybody. Cube. All right, here's my cube. A cross section is when you take a polyhedron, a 3-dimensional figure, and remember these from Unit 1, back when I barely knew you and probably liked a lot of you, not all of you, and that's gone out the window. Plane, right? A plane. So you take a polyhedron and a plane, and you take the plane and you slice it. Could be horizontally, vertically, diagonally. All right, so I'm going to take my cube. Ready? I'm going to slice it vertically. It's going to cut into 2 halves. I'm going to show you the 1 half. What 2-dimensional figure would be staring you right in the face? So let me do that again. I'm going to slice it vertically. Pretend it's sliced all the way through. I take half of it, turn it around, and show you. What shape am I showing you? That's a cross section. Okay, that is a cross section. Here you go. Visually, a lot of hands on today. Okay, here's a rectangular prism. Notice I'm slicing it with the plane horizontally. Really, no matter how I slice this, it's always going to be a rectangle, right? Okay, is that the case for every figure? How about a cylinder? Notice I cut it horizontally. I hold it up, it's a circle. What if I did it vertically? Am I going to get another circle back? Think about it. Cylinder, slice it. I open up 1 half and show you. What do you think? What's it going to be? Boom, rectangle. Okay, it's going to be a rectangle. So that is a cross section. Taking a plane, slicing it, either horizontally, vertically, at any angle, and then saying, all right, what do I have left over? All right, what 2D figure do I have left? So go back. I got a couple examples up here. Make sure we get the hang of this. So which figure can have the same cross section of a sphere? Well, whoa. As a sphere, will it matter? Doesn't it usually matter how I slice it? Because I might get a different figure. For a sphere, what do you think? Will I always get the same cross section with the sphere? What do you think? Let's try it. Let's go to the sphere. Spheres. All right, looks like I get a circle. Is there anything else I get other than a circle when I cut it? Nope. So I'm always going to get a cross section of a circle. So now which other of these 4 figures will I also get a cross section of a circle? Okay, only one of these will I get a cross section of a circle when I cut it. And that would be which figure up here? Woo! 17? 2, the cone, yes. If I take a cone and slice it horizontally with a plane, I will get a circle. All right, speaking of a cone, let's up the difficulty level now. Which one of these 4 would I never get as a cross section of a cone? All right, gotta think about a cone where I cut it this way. Which one would I never get? Well, we already said we're going to get a circle, right? So we can eliminate 4 from our discussion. All right, which one am I never going to get? Well, why don't we take a look, huh? Cone. That's where I get my circle. Everyone ready? The suspense is killing. Circle, 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 circle. Whoa! How about that bad boy right there, huh? The little arch, huh? Yep. Anybody think we can't get that? Or we can get that. Let's keep going, though. Let's keep going. And what do I end up with a vertical slice? Triangle, right? And now I know it seems weird, right? I can never get a square from that, but it's true. I can never get a cross section of a square from the cone. All right. So any issues on faces, edges, vertices, or cross sections? Now we go into what we're talking about this unit, which is lateral and surface area of polyhedrons. I talked to you before when we did number 3, and we said it was a prism, and then some people chimed in and gave it a little more detail and said it was a triangular prism, which is correct. So now my question is, I didn't do it, did I? I don't think I did. Didn't want to deny you the transition. How do I name a prism? Here you go. Here's a bunch of prisms up here. Triangular, square, cube, rectangular, octagonal, hexagonal, pentagonal prisms. What do you think? How do I name a prism? I look where? Be careful there. Because if I take a cross section of this octagonal prism going vertically, it's going to be a rectangle. And that's not a rectangular prism. Need a little bit more. What could I name a prism by? Octagonal, hexagonal. What are these two here? Bases. I name a prism by its bases. Okay. Now, how do you know that's the base, right? Why couldn't that be the base if I set it on the ground like that? Okay. What are bases first? Bases, and it's in the definition here. In a prism, bases are the only two figures that are parallel and congruent to each other. That's how you identify bases. All right. You find the two figures that are congruent and parallel. All right. All right. Now, here comes the good stuff. What is the difference between lateral area and surface area? Lateral area. How many bases does each prism have? How many bases? 2. Take them off. Pretend you're in a prism. Take off the bases. What's left over is the lateral area. So it's the area of all faces excluding the bases. So I take off the bases. Whatever shapes remain, I find the areas of all of them, add them together, and you get the lateral area. All the faces excluding the bases. We're rhyme time here, huh? Poet didn't even know it. That's always a good one. I love that one. Bro, you got that. Zach, you're still thinking. It's okay. Okay. Surface area. That's everything. That's the area of every single face you have. All right. So that's the area of all faces. And it will be very clear once I do this problem below. I know you guys, I didn't change my notes from last year. I know you guys just have number 2 right now. Just let me blow this bad boy up. Everyone good? Area of all the faces? I'm just going to blow this up, put this down. All right, so for the first question, what do I call that? What do I call that prism right there? That's a what type of prism? Talk to me. Talk to me here. 23, what type of prism? Triangular, right? Because it's got triangular bases. So part A says, all right, let's find the lateral area. And I'm always going to abbreviate lateral area LA, okay, instead of writing out the word. Hey, guys, I don't have a formula for you. I don't. I want you to understand the concept of lateral area. Maddie, again, what shape are the bases? Everyone take them off right now. In your mind, take off those triangles. How many faces are left? How many faces are left when I take off the triangles? 3, and they're all in what shape? Which you know how to find the area of. So here's how we're going to find the lateral area. Length times width, plus length times width plus length times width. You are going to find the area of all three rectangles, and you will have the lateral area. All right, let's do one of them. Tell me the length and width of one rectangle you definitely know already. 28. Tyler.
12 and 16.
The bottom base, right? The bottom face is 12 by 16. This one right here, I'll highlight it in yellow in case you didn't see that. 12 times 16. All right, ready? Plus, give me another bit length and width you know of, another face. 7. I knew it. 27. 9 and 16. Without doing a thing, that's this base too, by the way, the one on the left. Without doing a thing, we know the area of 2 of the faces. Now, how about this third one, which is over to the right here? All right, I know, yellow. I at least know it's 16. Black, thank you. I at least know it's 16 by something, right? But that something's blank. But come on now. May 11th. 28. Tyler, how do I find that other side? The Pythag. Huh? Or Pythagorean theorem, or just Pythag. The Pythag. That's the first time I've heard that. Yes, the Pythag. Plug that 9 and 12 in then for me. 21. Where's the 9 and 12 go?
9 plus 12. Or A and B.
Thank you, Dan. Yep. 9 squared plus 12 squared equals c squared. I'll let you guys do your magic, and you let me know what that other dimension is. It's heating up in here. I love it every second. Just get hotter. Another month, we'll just be sweating profusely in here. 22. What's that other dimension?
C is equal to 15.
15. Thank you, Pedro. 15. And there you go, everybody. There's your lateral area. So you take off the bases and you find the area of everything that's left, which, yes, usually it'll be rectangles left over. Usually. As long as we're talking about prisms anyway. What you get for the lateral area? And we're still not done. 4, lateral area. 576. And if some of you that are into units, it is inches. What did we just find? Lateral. So it's got to be squared if you're going to do it, right? Still do an area, just in 3-dimensional space now. Oh, part B though. Now find surface area, which I'm going to abbreviate SA. How many total faces does this have? 5, and you already know the area for 3 of them. So I'm going to start my formula off with that 576 we just found, plus what are the 2 other faces we haven't calculated the area for? Maddie, they're what again? Triangles. And there's 2 of them that are congruent. So 2 times the area of a triangle. Oh, good thing we just had unit 11. 2 times 1/2 BH. And before some of you calculator whizzes, doesn't the 2 and the 1/2 going to cancel? Yes, they will. You can just put BH. Fine, you got me there. All right, go ahead. I'm sure that would have, and I would have heard your voice would have sounded just like that. Plus 2 times 1/2 times, what's the base and the height of one of those triangular bases? It's a right triangle. We did talk about that. The base and the height of a right triangle are the same as these. And what do you got for me? 11?
12 and 9.
The legs. There you go, everyone. So there's surface area. And what is that surface area when you find it? Oh, 11 again. 684 square inches. Hey, are we all good with this concept of what lateral is versus surface area? Because I need to talk about a special prism now, a special one. All right, special prism, which is a prism where the bases are circles, aka cylinder. All right. There is a formula because well, let me do it this way. All right. So lateral area, I take off the what? The bases. Done. I take them off. Still left with cylinder. right? That doesn't help me finding the lateral area, all right? So I need to give you a special formula for it, all right? One that you're gonna have to remember, it's not on the formula sheet, but I am not going to give it to you. You guys are gonna find it for me. Lateral area, I took off the circle bases, they're done. So this is what I have left. It still doesn't help me, it's a cylinder, so let me cut it open for you. What is the lateral area? It's actually a what? It's actually a rectangle. Close. It's actually a rectangle. Close. Yep. Everyone agrees? Lateral area, when I cut it open of a cylinder, is actually just a rectangle. That's all it is. You guys know how to find the area of a rectangle? What's the area of a rectangle? Base times height, length times width. But I'm not going to write that up there. I want more. I want more detail. So let me fold it back up for you. Remember? Length times width. Let's start on this. What was this? Ready? What was this of my cylinder? That's also known as the height. All right, so height is going to be involved. Let's go to the other part of the rectangle. Ready? We got this was the height of the cylinder. Don't yell anything out. What was this part? Let me fold it back. What was that part? All right, you're going to have to go back to unit 10 for this one. What was this called again? This distance? Go ahead. Circumference, yes. So this is the circumference, this is the height, but I'm not going to put circumference because you know the formula. Who's going to dig deep there? Circumference. Dylan? Pi d. So what's the lateral area of a cylinder? Everyone put them together. I just spent like 3-4 minutes doing this visual here. What do I have here? Pi d times height. There we go. Pi dh is the lateral area. And there is no way I'm going to provide the surface area formula for you. Because what's just surface area? Put back on what? What am I going to reattach? 2 circle bases. 2 circle bases. Talk to your group. Where do you think the whole formula is written out of a surface area of a cylinder? All I'm doing is taking the lateral area, and putting on the 2 circular bases. Write it all out for me. Come on. Come on.
There's 2 circles.
Two. Who's got 2? Is our group confident here? I don't know, but that's why I'm asking because I called on Phoenix. So I'm asking is the whole group confident?
Thank you.
All right, what do we got?
Diameter times height times pi.
Oh, okay. So pi dh, which is your lateral area. Yep.
Times 2 pi r squared.
Almost. Do I really want to multiply them?
Oh, plus.
I'm attaching them, right? Adding that on to 2 pi r squared. Yep. There we go. All right. Again, not provided on the formula sheet. You can take a look. They're not there. All right. So here we go. Just some quick problems here. There's one trap I don't want you to fall in, which I'll talk about it when we get to it. Find the lateral area to the nearest tenth. So I got pi dh, lateral area, not surface. I already gave you the diameters 10. Now look, I know Oliver's going to just plug in 2 because that's the remaining number. But you've got to understand, though, what makes a height. What makes the height of a cylinder or any prism? It is the side or edge that connects the bases. Whatever is connecting the bases of a prism or cylinder is the height. In this case, yes, it is 2. Whatever connects the bases is your height. And I'm not even going to waste your time or mine. 62.8 square centimeters. All right, next one here, pi dh again, just to make sure we're good. Diameter, anybody? Diameter? 6, yep, good. You can double a radius, excellent. And then 6 again for the height. You see what I mean by height? Connects the bases. And then I type all that beautiful stuff in my calculator, 113.1 meters squared. Anything before I go to surface area? All right, next up, surface area. Wow, it is really heating up in here. I love every minute of this. Surface area. I got people wiping off sweat. I got people fanning themselves. I got Rip Van Winkle falling asleep again in the back. High DH. Wake up pretty quick with the throat punch. Yeah? Wake up pretty quick. Plus 2 pi r squared. That might be the best nickname I've come up with in at least 5 or 6 years. All right, in all seriousness now, watch out for this trap when you do surface area of a cylinder. And you may not think it's a trap, but if you're going pretty quick, you may fall into it. One part of the formula has diameter, the other has radius. I will see a lot of students just put the same number in. Okay, because they're not thinking diameter and then radius. All right, so pi 2, right? Diameter 2 times 3, and then all of a sudden, now I need the radius, not the diameter again. So 1 squared. Make sure you put diameter into the left, radius into the right. Ooh, anybody notice the directions? In terms of pi, Tyler, yes, in terms of pi. Oh, I want to make sure we're good with the algebra. 6 pi and 2 pi. Unlike some of the problems from last unit where I left your answer in terms of pi, can we combine those? Yeah. Both of them have pi's. That's fine. It's not like it's 6 plus 2 pi and I'd be done. So the answer here, yeah, the surface area is 8 pi meters squared. Okay, 8 pi meters squared. And then our final cylinder here. I just have a habit of writing the formula. I'm not expecting that from you. All right, pi, diameter 7, height of 10. Again, I'll see a 7 plugged in here and see 7 squared. Take your darn time and notice half, one part's diameter, other part's radius. So I should see a 3.5 squared, not a 7 squared. So what do I have there? 70 pi plus, what's that, 24.5 pi? Combine them? Yes, I can. 94.5 pi centimeters squared. And then we get to my favorite part of class this unit, which is the end, where now we take whatever figures we have talked about that day or have talked about in previous days and just smash them together and say, what is the surface area of this smashed up figure? First, we got to know what they're asking for here. Surface area. I want to make sure we know what this means. This isn't just going to be cylinder plus cube, add them together and I'm done. No. Surface area. What is showing? What is showing, not covered up, is the surface area. How many faces does this cube have? How many faces? It's not a trick question. 6. Are all of them showing? Fully showing? All 6? No! Look at the top one. The top one's not fully showing. It's being covered up, part of it. But what I still need from it is this part here. That's part of the surface area. So it's just not going to be cube plus cylinder and I'm done for the day. It's what's exposed, what's on the outside, what's not covered up. That's the surface area. All right, so let's start with the cylinder. Usually, this is what I would use with you guys, right? Pi dh plus 2 pi r squared, surface area of a cylinder. Is the whole cylinder showing? No, it is not. Part of it is covered up. What part is covered up? One of the bases. So can somebody adjust my full surface area formula to what I'm going to do here? Because one base is being covered up. I can't count it as part of its surface area. It is covered. It is covered. So adjust it for me. Oh, 7. Got it. 22.
was the question?
All right, you ready, Pedro? Is the full cylinder showing?
No.
What's covered up, Pedro?
Oh, one of the bases.
So I don't want to use the full surface area formula.
Yeah.
If you said one of the bases is covered up, what should I not be doing here? Adjust this.
You shouldn't multiply it by 2.
Darn right. It should just be plus pi r squared.
Yes.
Good. So everyone all right? Because the cube is a whole different beast. All right. Pi. All right. Whoa, whoa. What's the 4 pointing to? Because this is going to happen tonight and future nights on in your textbook. What is drawn in? So that's what that 4 means. All right. I know some of you may look at, oh, it's pointing to the radius. No, no, no. It's pointing to whatever is drawn in. So if it's a radius, then I'd only have that drawn in. This is a diameter of 4. What's the height? Remember, what's connecting the bases? 4, right here. Here's your height. Plus pi, radius, 2 squared. That's half of it. I have to add that to the cube when I get to it. So whether you guys leave it like this, if you want to go nuts and simplify it, I don't care. You're going to have to add this to the cube eventually. So I don't care how you leave the cylinder. That's not your final answer. But I go hardcore if I can, right? 16 and 4 pi, 20 pi for the cylinder. You don't have to go that far. All right, you guys ready for the cube now? Because there's a couple different ways we can attack the cube. You guys said there were 6 faces. How many are fully showing? 5. So let me start it off this way. And again, we can do it another way. So cube. I have 5 faces, and they all have the same areas. It's not like I have to do this one plus this one plus this one. They all have the same areas because it's a cube. How do you find the area of one of the faces? 2, area of one of the faces.
Oh, you multiply the length by the width.
Which would be what in our case?
5 by 5.
Okay, so everyone good? 5 times 5, full faces. What about the 6th face? How do I find the area of the 6th face? Meaning, basically, the shaded in region here. How do I find that now? Plus the whole thing, right? Whole minus, right? Whole 5 times 5, and then what am I going to subtract out? What do I need to subtract out from that face? Minus pi r squared. Anybody think of doing this another way? I could do this. Or, ready? Or I could just do all 6 faces, but instead of adding, subtract out the circle. It's up to you. But does everyone see where I'm coming from as far as what surface area actually is? It's what's showing. You can't count things that are covered up. And so this is what? 6 times 5 minus pi 2 squared. And my last question before I call on somebody for the final answer, how do you find the total surface area now? What do I need to do to the cube and the cylinder? I want to find total surface area. What do I need to do to 20 pi and whatever this comes out to be? Add them up. Okay, I'm going to add these up. This is where I need you to be in this honors level class. Is you can do a separate cylinder and a separate cube perfectly, but now when I put them on top of each other side by side, what's covered up, what's not. When you're ready, let me know. Oh, let's go nearest 10th. Sorry, I should have did directions. Nearest 10th. 9. Generator knows.
200.3.
There you go. Questions? All right. There's only 5 problems tonight, and the packet on the next page, which deals with cross sections. So instead of grabbing a book, why don't you guys at least get that packet page done, and then worry about the textbooks tonight.